In FTC Robots Revealed, we get an up-and-close look at how different mechanical mechanisms work on world-class robots.
We actually have a little trigger back there that extends out of the ramp.
And today we're taking a look at Team 10084 Calamari. We're joining them at the FTC DECODE World Championships for the 2025-26 season. And some really interesting mechanisms to take a look at are some concepts of brake pads, so that when they have to shoot, they layer a brake pad down so they can't get moved around while another robot is trying to shoot them.
We have to have brakes on the bottom of the bot to help counteract defense.
They've got a really efficient intake as well as a ramp to get some high throughput.
The artifacts will just be pulled in.
They've also used some really interesting materials to get a counterspin roller on their hooded shooter as well to make their shots a lot more accurate.
And what is this counterspin roller made out of? Is it...
So that's made out of TPU air.
Let's start off. Let's talk about your drivetrain. You're clearly a hooded shooter, but what's special about your drivetrain? You guys got something unique you added on there.
Yeah, so the drivetrain is just a very, very simple parallel plate. Instead of opting for 435 motors at a 1-to-1, we actually opted for 312s at a 1.5-to-1. So that boosts us a little bit over the 435 RPM, which just gives us a little bit of extra speed. We also opted for simplicity, so we haven't had a single drivetrain failure this season. It's just been consistent the entire time, all the way throughout the season.
And it's driving with some little G2 here, or is it HD5?
HD5, yeah.
Okay, yeah.
And then since the drivetrain doesn't have very much torque because we opted for speed, we have to have brakes on the bottom of the bot to help counteract defense. So what that allows us to do is when we go to line up to shoot, we can deploy those brakes, and it actually gives us the ability to fend off bots that are much heavier or have a lot more torque than us. But we can pull them up as soon as we're done firing, and we can go off speeding around the field due to the fast drivetrain.
And it's got an axle that's running all the way through it. What is actually making that brake pad shift up and down? Looks like you've got a little 2-bar linkage there.
Yeah, the axle is actually just a dead axle, and then it's just a simple 3D printed collar around it.
Yep.
And then just a simple 2-bar, or not 2-bar, it's just a single bar linkage right there, just to deploy the brake pad.
Yep.
That was just simply for space constraints. The back one's a lot more simpler, just direct driven, straight to a 35 kilogram centimeter servo.
Does this front one over center as well? Or
it does not.
Just presses down. Okay. And then it looks like you've got like grip tape that's just sitting on top of that, yeah?
Yep, it's actually used for commercial applications like putting on steps and things to keep people from slipping. But we find it works very, very well for just gripping against the field tiles, and it doesn't cause any major damage. It can leave a few scuffs sometimes, but it's nothing that just like rubbing it out with your foot can't help.
Yep. And then you've got one last little thing on your drivetrain there. Is that your parking, I'm assuming?
Yep. Okay. So we call that the tipper. That'll tip us up onto our side so we can do a full park while only taking up a little bit of the square.
Yeah.
After installing our brakes, we also found that we can use the front brake in tandem with the tipper to actually tip backwards. So if we do that, it will actually kick this out right before it launches the tipper down, and that'll actually tilt the robot back just enough that we can actually tip backwards into the square. So we have a few parking options.
That's super creative. I love that. And then as a random little sidebar here, one, I love that you've labeled your motor on the inside there. So it sees that as E2, and then it looks like you 3D printed little caps on top of the motor as well.
Yep. We actually saw that from another team last year, and we realized that they go build the caps. They actually have a little bit of dead space in them. And just for extra compactness to be able to fit around this ramp, we contoured the caps completely around the motor, and there's even a tiny little bump on the back of it to act as a relief for the encoder.
Awesome. I love it. I always love when you got those tiny little extra bonuses. Let's talk about your intake then. How does that work?
Yeah, so we've actually gone through a lot of intake iterations. I don't know if we have the judging. There we go. Yeah, so we actually started out originally with just large printed TPU air wheels. These were servo driven, super, super slow on our first scrimmage bot. But we like the concept of them because they're very simple and very reliable for linearly pulling artifacts in. So then this was our V2. It was just a smaller, but motor driven, so much faster to be able to pull those artifacts in. But it had very little grip just because of the material. So we actually coated them with a high friction coating called rubber cement. And that gave us the ability to really quickly pull artifacts in. But trying to intake 3 artifacts in a line here, we weren't able to do that because these wheels also have a lot of friction side to side like this, not only forward and backward. So those switching to surgical tubing, they're able to freely bend to the side like this. So when we actually do need to intake 3 in a line, the artifacts will just be pulled in consistently by the surgical tubing.
Cool. And then transfer-wise, you've got... Is this the leftover wheels that you did before? And then you just cut the edges off of them? It's little flapper wheels? What are those little guys?
So we did originally start with these as our main transfer wheels. But what we found is since they're under really, really high compression as the artifacts move through, these will get torn up very quickly and were bad for longevity. They also had a little bit too much friction. So when we had to intake in 2 artifacts, the motors would stall out a lot sooner. So we opted for a more gentle, just flapper wheel like this. It gives it a little bit less friction just so the motors can spin more freely, or the motor can spin more freely when multiple artifacts are intaken. And they're also much better for longevity.
Yeah, so it really doesn't really grip it hard, but it clearly moves that artifact up, no problem. Now that last little scoop up, how do you get it past that angle on that last little scoop? So like what actually gets it up and into the turret? Because that's a challenge a lot of teams have come up with.
So since our transfer is really, really fast, the actual inertia of the artifacts is enough when firing 3 to launch them up. But in the case that we intake slowly, or if we intake slowly, and there wasn't enough inertia, or if we're just single firing, say if we wanted to like sequence an endgame or something, we actually have a little trigger back there that extends out of the ramp that just gives us a little bit of extra, just a little bit of extra push up, just in case we have like a jam or something like that.
Yeah, it's just not quite able to get it up into that. But then when you have 3 in a row as they're moving up, they can force themselves through.
Exactly.
Cool. And then let's talk about your shooter then. What did you come up with for your hood?
So yeah, just like with most of the other mechanisms on our bot, we started out with our first shooter, which was a very just bare bones, no counter spin adjustment or anything like that. And we found with that we needed a little bit more trajectory adjustment because we just had a little flap on the top, but that wasn't nearly enough to actually make the artifacts take a different path. So now what we have is an adjustable hood that gives a full 20 degrees of range that we can change in terms of just like, if we want to shoot from the far zone, we'll put it up, get more of a line drive. I mean, if we're shooting from close, we'll put it all the way down and kind of just lob them up just to get them over the goal. And then we also have active backspin cancellation up there with a custom printed TPU roller.
So you've got these little 3D printed gears that are running through this belt, through this other belt, and then there's a full motor for that backspin roller?
It's actually, we have 2 full 600 RPM motors on the back.
Yeah.
They're just hugged up next to each other. So the backspin roller is just kind of tandeming off this motor on the left right here.
Yeah. Okay.
So it just comes off the left one.
So it's running at the same RPM as your flywheel then?
Yeah, but there is a pretty hefty, its initial RPM is the same, but there's a really hefty ratio right there between the pinion and the driven.
Yeah, that's fair. That's really creative. I love when you can tie together axles and belts and share that out a little bit. And then you've got what looks like aluminum foil tape, or is it duct tape?
That is aluminum foil.
Okay. Yeah.
That's just to make the hood a little bit more slippery. So as the artifacts are going up, they're not inclined to spin backwards and make backspin more of an issue. Because we had a lot of issues with that before we added things like the counterspin roller and then aluminum tape.
And what is this counterspin roller made out of? Is it?
So that's made out of TPU air, which is it's kind of like a sister filament to TPU.
Yeah.
Except it actually foams up when it prints. So it gives you this really, really porous, flexible material that has a little bit of natural grip to it. So instead of having to add like the coating like we did on those other wheels, it's actually able to just compress enough that actually gets enough grip on the artifact to be able to cancel some of that backspin.
I love using new tech in there because TPU Air just came out like 6 months ago.
Yeah, so Stratec just came out with it. Yeah. And we saw it and we were like, it looks very usable.
We also contoured it so that it would fit perfectly to just get maximum grip as well.
Mm-hmm. Super slick. And then what kind of driver automations do you got going on? How do you make life easier for your drivers?
So we have a few things going on. One thing is automatic turret aiming. Obviously, we have that to to minimize human error in that respect. We use a combination of odometry and limelight tracking to get maximum consistency. Just that way we're always locked onto the goal properly. We also have automation. We have a regression that automatically adjusts the hood and the launcher motor based on the distance from the goal, or well, actually a point inside the goal. That way we...
You just have like a Y lookup table for that? Like a Y lookup table for that? Or
Yeah,
linear
so
interpolation?
so we did. We took like 6 or 7 points across the close and far zone, and then put that into a line generator to get the questions. And we use a fifth order polynomial for close zone and a asymmetrical sigmoidal function for far zone because it fits the line best.
Another quality of life we have for the driving is communication on when some certain actions should be done. So the driver control actually on their right bumper, this deploys the brakes as well as also rumbling the launcher driver's controller. So when this is pulled, it will deploy the brakes and then it also rumble that controller so that he knows to fire when we're in position. And then the opposite is also true for when we finish our launching sequence. So when that trigger is deployed to kick up, that also sends a vibration to my controller to tell me the launching sequence is done. So if I'm looking somewhere else on the field, or just leave my order to get artifacts next, I'll feel that vibration when we go.
Very cool. And then what are you guys most proud of on this robot?
I would say that what we're most proud of is our launching consistency. We've worked a lot. We've done a lot of PIDF loop tuning and a lot of tracking adjustments and rewriting the tracking code, and we've gotten our consistency really, really solid. So close zone, we got like 91% accuracy in teleop, and then far zone is probably close to that. We haven't checked, like actually calculated it out in a while. And then in autonomous, we had 98% accuracy in close zone. So I was
super impressive.
We were all pretty happy with that. Can't get much better than 98% in my opinion.
Oh, thanks so much for sharing this, guys. I hope you're proud of your work, and it's awesome robot.
Absolutely. Thank you.
Yeah, thank you.